Hi everyone, my name is Shubhadeep Roy. Here I am introducing our work on test time adaptation for blind image quality assessment. My collaborators are Shankhanil Mitro, Soma Biswas and Rajiv Sundarajan. We are all from Indian Institute of Science. Here, the goal of blind image quality assessment is to predict the perceptual quality of an image without having access to the reference or clean image. There exist several machine learning and deep learning based methods to predict the qualities of an image, but all these methods suffer from the problem of distribution shift. So here you can see there exists distribution shift across various image query databases like images having synthetic distortion or authentic distortion or generated images coming from some image restoration task. So to mitigate this distribution shift, we need test time adaptation. To solve our problem, we have to adapt the model. But in practical scenario, it happens that the source data may not be available. So without having source data, how we will adapt our model? So what we will do, when a batch of unlabeled test data arrive, we will update the model parameters by learning some self-service auxiliary tasks. But here are some challenges. In literature survey, all the testing adaptation techniques are based on maximizing the class prediction of different levels, which is not applicable for quality assessment type of regression task. So we need to design new self-service auxiliary tasks which can learn quality related information from the model. So in our method, what we will do? First we divide the whole model in two parts. One is the feature estimator part and another is the quality reducer part. During adaptation, we only adapt the batch normalization parameters of the feature estimator, keeping the quality reducer frozen because we want to learn the distribution shift and batch normalization parameter can be helpful for this purpose. To avoid overfitting, we add a simple fully connected layer as projection head. So here our main contribution is to design these two auxiliary tasks, that is rank loss and group countership loss. So first let us discuss the rank loss. When a test image will arrive, we will add to different level of degradation by adding synthetic distortion, for example Gaussian blur, or adding white noise or compression. Ideally we want that our model can learn this distance between highly distorted version and the original image should be higher than the distance between lesser distorted version and the original image. For this, we first extract the features from all these three images using the feature extractor followed by the projection head. Then we calculate the equivalent distance between these features and we calculate the probability that the distance higher should be greater than the distance lower. And we use this probability to calculate the binary cross entropy loss, which we will be used as a rank loss. On the other hand, in group countership loss, we first use the knowledge of the source model to create two different quality groups. We use the predicted quality from the source model to sort the images and make two different groups by picking some top p% from both the end. Here our target is that the images coming from the same quality group should become closer and the images coming from a different quality group should be pulls apart. So for this purpose we use the contrastive loss to learn the quality difference between two different groups. Here in quantitative analysis we can see our test generation techniques can outperform the baseline performance in all the four models and also for all these four image databases. So here we use both the rank and group countership loss. But why we need both the losses? Here you can see when an image is highly distorted, adding more synthetic distortion cannot be perceptually distinguishable. So in such cases, rank loss may not be effective. On the other hand, when in a batch, most of the images having similar quality according to the source model, it is very difficult to form two different quality groups as the source model predictions can be erroneous. So we cannot rely on it. In such cases, rank loss may be more useful by creating two different degraded versions of the same image. So we can conclude that our proposed test generation method can give significant improvement for blind image quality tasks using these two self-service auxiliary tasks using rank and group countership loss. In future, we can extend our idea on online testing adaptation techniques where test data is coming sequentially and model may face the issue of catastrophic forgetting. Also, our idea of image quality assessment can be further extended to video quality assessment. Thank you all.